Okay, these are your 5.1 notes on the quadratic function and its different forms. So we're looking at today as what we call equivalent forms, so we can talk about three different versions of the quadratic function. Now, we did talk about the quadratic function in chapter 4. The parent graph for that is your x squared graph. We may not use the word quadratic so much, but definitely talked about the graph as being a parabola and having a vertex and just some of the basics of that, and using that as one of our many graphs that we talked about with like translation and reflection and that kind of thing. So today we're going to get more of a deep dive on this and talk about just the quadratic and go a lot more detail on graphing and how we convert forms and equation writing. That's kind of basically our three big things to do today. So let's start out by looking at the three forms. We've got vertex, general, and factored. We're going to go ahead and move forward here and show you those. First of all, what is it that makes a quadratic is the fact that you have x squared in your equation. And as you look through here, you might go, well, I see x squared here. I don't exactly see it here, and I don't see it here at all. But if we were converting these two forms, the first two, into general, which we'll do, you'll definitely see that x squared showing up. And actually here it is there. That's x squared right there. So the form you guys will be familiar with from chapter 4 when we did transformations like left, right, up, down, reflect, dilate. When we did quadratic, or the x squared family, we did left, right, up, and down. So h and k should be familiar to you guys. Factored form is one we have not worked with yet. Generally, we have. It's just kind of been sort of here and there with a little bit of factoring discussion earlier on in the course and stuff like that, but not so much as a graphing problem. So our goal today is to work through the forms, see how we can turn one to the other, definitely do some graphing, and build up the idea of what a quadratic function looks like in all of its details and its forms. So let's go ahead and start with that. So let's break down the graph. First of all, we've got a vertex, which you guys are familiar with. In this case, our vertex sits at 0, 0. It's also the place where our graph would change direction, so we're decreasing here. As we hit that vertex, we change to increase, a concept from the past. We've got a line called an axis symmetry. The axis symmetry is a line that would visually cut the graph in half, give you two equal halves left and right. So that actually runs right down through the vertex. Those ideas are connected. We've got a max or a min value, which basically means where is your vertex located. Is it a max or a min? Now in this case, max or min means y value, so this would be a min. This would be your smallest y value on the graph. There are larger ones as you go in either direction. How we graph is based on a pattern change, so we're going to get away from tabling, where we're plugging in values and just trying to generate a set of coordinates, and use a pattern change, which actually is much smoother and quicker once you get used to it. If the number a out front is positive, let's talk about that first. The positive a value would cause your parabola to open up, so this is an opening up parabola. If that a was negative, if you guys think about how that ties into chapter 4, if it was a negative a, that would cause a reflection. If you reflected this graph over the x-axis, then it would sit down here, and that would be opening down. So really a negative a is nothing more than a reflection of this graph over the x-axis. Now getting back to the pattern change, how that works, so when your a number is a 1, which this graph has that going on, I'll throw that axis symmetry back in. When your a is a 1, your pattern change will be 1, 3, and 5. The first number in the pattern change is based on the number that sits out here in front. So if this number is a 1, you have a 1, 3, 5. If this number is something other than 1, so a is not 1, let's say it's like a 2, for example, you're going to multiply these three numbers by 2. So let's say you had an a value of 2, you'd have a 2 times 1, 3, 5, which would give you a 2, 6, 10. We'll hit all that in a minute. Let's just see how the pattern change works. So what I've got over here is a description with arrows. This is how you would say it to yourself as you do it. So if you look at the arrows, it says go over 1, then go up 1, starting at the vertex. So the first number in the pattern change is 1, so I go over 1 and up 1, plot a point. In the second set, I go over 1, up 3. You notice that the ups are your 1, 3, 5. You're always just going over 1. So I go over 1, up 3, and plot a point. And then again, doing these from the vertex, right? So over 1, up. From the vertex, over 1, up 1, over 1, up 3, and then just continue on. So we go point to point, but start the vertex, then go point to point. So that last one is going to be over 1, up 5, which would put us up here. Now, because the graph has what we call symmetry, which is what that axis symmetry is telling us, we can plot points that would be on the opposite side that, of course, would match that or be a mirror image of that. So there's your 1, 3, 5, your pattern change. Over 1, up 1, over 1, up 3, over 1, up 5. Okay, and that's all of our details with how we graph. Again, pattern change is much easier to use than having a table. Once you get the idea of the concept of pattern change down, you guys will like that. It'll make graphing a lot easier. All right, so in comparison, like a minute ago, I was just talking about a 2, 6, 10. So again, just showing you quickly how it works. If I'm doing a 1, 3, 5, I go over 1, up 1. And then starting from that next point, over 1, up 3. and then started from that point over 1 up 5. And there's my 1, 3, 5. And again, I'd have symmetry, so I would graph points on the opposite side of the axis of symmetry, which I don't have drawn here, but that's okay. That would sit visually right down through the origin here. Now, at 2, 6, 10, on the other hand, they're all over 1s, right? So it doesn't make a difference what the pattern change is. It's always over 1, and it's up or down by these numbers. So I will still go over 1, but since my first number in the pattern changes to 2, I'll go up 2. And then from that point, I'll hit the next one, so over 1 up 6. And then from that one, over 1 up 10. And then again, the symmetry idea. Now, typically when you're graphing with a 2, 6, 10, we probably just use 2 and 6. We usually won't go out to 10 because by that time you're getting so far off so high up or down on the axis that it gets to be kind of, well, just not necessary. You know, if I had these 5 points, I can draw the graph pretty easily. I don't necessarily need these 2. So probably just do 2 and 6, but if you have space, you can do the 10. So again, just to repeat, it's over always by 1, and then up 2, 6, 10. Okay, so that's how our pattern change works. Let's get into doing some converting and graphing. So we're going to start out with our vertex form, and you guys should, again, be familiar with this one. The first thing to do when you graph vertex form is, of course, find your vertex. Now, when chapter 4 would discuss this as a translation, so we'd say, well, I'm going right and I'm going down. That's fine, but we're not starting with a parent graph. We're going to go right into graphing this, so we're not going to work off a parent and move it. We're just going to say, hey, where's your vertex at? And then use our pattern change to help us out. Your vertex here would be 2, negative 5. Remember that when you go from parentheses to coordinate, that's going to be a sign change because basically you're solving that little expression right there for x. So there's your vertex, 2, negative 5. X is symmetry. Would actually run right down through the x value of the vertex. That's why I have those two kind of highlighted. So here's the axis symmetry. The fact that you got a 1 out front here, a positive 1, you don't see it, but it's a positive 1. That means that your graph's going to open up. And because this is a positive 1 out front, your pattern change would be a 1, 3, 5. So there's that 1. Again, that 1 won't be there, but we need to understand that that's a 1 there. And then, again, how I did the pattern change is over 1 up 1, over 1 up 3, over 1 up 5. And then I can duplicate that on the other side, or once I've done like the right side, for example, then I can just do a mirror image of the points and then go ahead and see my graph. Going to general form is really just an algebra process. So this is not general, right? This is vertex. And what I'm going to do is start out with that original equation. And I'm going to just start doing what the problem sort of says. So I'm going to square it. Remember, squaring means to multiply something by itself. So that means we're going to take x minus 2 times x minus 2. So multiply it by itself. The negative 5 we're just going to bring with for a little bit. This now becomes a FOIL problem. So I do my first x squared, my outside and inside are both negative 2x, so combine them. My last term, positive 4. Still bring that negative 5 with, then the very last step is just put these two numbers together. And now I've got it in general form. So turning into general is just a matter of you being able to do the algebra, and I think we all can do that. Just follow those steps and you're good to go. So there's graphing out of vertex form. Again, pretty easy to do. Grab your vertex. Axis symmetry is not something that has to be graphed, but I think it doesn't hurt. I think it helps you visualize what's going on. Determine which way it opens, what's your pattern change. Again, much easier and quicker than trying to generate a bunch of coordinates by tabling. Especially when we have a graph that's been shifted. It's just easier to use a pattern change. All right, let's talk about some others here. So again, a little more practice will give you a little different pattern change this time. But again, first thing to do is grab my vertex out of there. So I'm going to grab my vertex. Remember, from parenthesis to coordinate, sign change. The k stays the same. So there's my vertex up there at negative 1, 7. Axis symmetry just runs right down through that. So again, the connection between the vertex and the axis symmetry is that it runs through the x coordinate of the vertex. Because this is a negative a out front, that means our graph opens down. And because this number is not a 1, we're going to multiply it by 135. So negative 2 times 135 would give me negative 2, negative 6, negative 10. And so you can see that number out front is the first number in the pattern of change. And then how I use it is what you saw pop up when I hit the pattern change is because it's going down now, I got to go over 1 and down by those numbers, not up, right? So over 1 down 2, over 1 down 6. And I didn't bother to do the 10 because that would run me way down here, and I don't need that many points to draw the graph. So basically a 2, 6, 10, over 1 down 2, over 1 down 6. And then again, mirror image on the other side of the axis symmetry and draw your graph. And there you go. Parabolas have never been so easy to graph, right? And then the conversion idea, get your graph turned, your equation turned into general form is the same thing I showed you on that last one. So we're going to take the original equation. We're going to do the foiling first, so don't worry about the numbers in black. Just get your squaring done. Think of it as order of operations, right? Exponents would be the parentheses and exponents, PEMDAS. Parentheses, exponents, the very first thing. in the list. Then multiplication, then addition, subtraction. So if you stick to the order of operations in your algebra, that should take you through that. So remember, squaring means to multiply something by itself. So we're going to take x plus 1 times x plus 1. Got to FOIL that out. So there in blue is that FOILed. And then distribute next the -2 into the set of parentheses. So now put that -2 in. So distribute, distribute, distribute. And then last thing, combine your two number terms on the end. And you got it in general form. Okay, let's keep moving. So let's switch over to factored. Factored is a little bit different. Factored form, we have what are called our zeros, which actually are x-intercepts. So the R1, R2 are zeros. It's not a vertex, so you got to get that idea out of your head. It's a different format, different thing to pull out of there. But what your zeros are simply are what are these numbers. Again, the way we do that is if we were solving these kind of these expressions as little mini equations, like set n equal to 0 and solve. But again, the idea of going from a parenthesis to a value where its sign changes, here's why its sign changes. Same as a vertex. But do not, this is a mistake that students make, is they find these two and then they write them together as a coordinate like it's a vertex. That's not what it is, right? These two numbers produce x-intercepts. They don't produce a vertex, so they're separate coordinates. So x-intercepts would be written as comma 0. So 1 comma 0, -2 0. Don't put these two numbers together into one single coordinate. So what I have now are x-intercepts. The axis symmetry, because I don't have a vertex, but I can still visualize, should be halfway between the two. So when I pop out my axis symmetry, basically what I'm doing is trying to space it equally between the two. That should always be the case. And it comes in at -1/2. When I go to the idea of the equation with that negative sitting out front right there, that means it should open down. And because this number is -1, then I got to multiply that by my pattern change. So -1 times 135 is -1, -3, -5. Sometimes when you run the pattern change from the vertex, you can hit this. Sometimes you don't. Now, in terms of how I got the vertex, so you might be wondering, like, wait a minute, those red points just popped up, but how do I know that's where the vertex is at? You know, the x-intercepts coming from my equation, sure, I got those, but how in the heck did I get that? Well, what I do know is the x value of the vertex is -1/2, because remember from earlier slides that I said that actually is a connection. So what that tells me is the vertex is -1/2 comma something, and then what I just need to do is do a little side calculation and find it. So what I'm doing is taking the equation that's sitting right here, and I'm plugging in what I know. So I know my a value was -1. It was right there. I know the x value from the vertex has to be the same as that value right there, which is -1/2. And then I got my other values that existed from the beginning, right? And now all I got to do is a little bit of solving. So this is -1.5. This is +1.5. Multiply all those together, and I get a y value of, and now I know that my vertex sits at -1/2 and 2.25. So sometimes this won't happen. You'll get a nice, neat way of having the vertex show up by the pattern change. But it isn't that you can always go from the blue points, the r's, or the x-intercepts and get yourself to this. Sometimes you got to do a little side calculation. That's how I would come up with that if I needed to. And then, of course, the last thing is, what's your graph look like? And then the conversion, again, just going back to that equation. And this time I'm going to start by just foiling it right out. So I'm going to FOIL those two. Then take that negative, distribute it in, and it should be done general form. Okay, let's go ahead and move on. Let's check out one more graph in factored form, and then we're going to get to equation writing and try to wrap it up here as soon as we can. So again, things I want to do is start right away, do a little bit of mini solving, right? Grab those zeros, turn them into x-intercepts. So again, I'm just taking these two expressions, solving them as kind of a mini equation. Axis symmetry, again, is visually halfway between these 2 points. So that's how I know where to place that. So I'm going exactly halfway between the two x-intercepts. The fact that it's a +1/2 out front tells me it opens up. Pattern change now would be 1/2 times 135. So that's 1/2, 3/2, 5/2. In this case, I can take it a little bit different. So the question here again is sort of like, wait a minute, how did I get the vertex, right? So before I had a calculation way of showing you, this time I'm going to show you a reasoning way of doing it. So what you can do is say how far is either x-intercept from the midline or from the axis symmetry. And it's 2 on either side. So if I know that it's 2 on either side, what the 2 distance from this point to the axis symmetry means that I have to get myself through the first two numbers in the pattern change. Well, if I add the first two together, 1/2 and 3/2 is 4/2, which is 2, which means the vertex has to sit 2 from the origin. And then I know this graph opens up. So that's how I know to place it. So that's another way to do it. Now this works nice because in this case, as I go from the vertex and run the pattern change, I hit my x-intercepts. If you don't hit them, that's not going to work. And then there's your graph. And then the last little bit of this is to do your conversion.